So this is one of the papers that, I mean, as I was saying, I was pretty happy that people are extremely brutal with that paper, right? But I hope to show you the positive sides of this stuff, right? So this is the citation they gave for putting this in the Hall of Fame, and this was inducted, I think, in 2006, so the second year or something. So this was like the third or fourth paper that they added into the Hall of Fame. And operating systems research has been going on since 60s or so, right? And this was relatively new. I mean, this is inducted 10 years after they were they submitted this idea. So somebody liked this paper enough that in 10 years, getting into the Hall of Fame, as the third or fourth paper, they deserve something, right? So one of the things that they cite is this is the first paper which talked about proof carrying code and what you can do with that, right? So I want you to look at it in that context, right? So this is one of those papers where people from some other area come to some other area and they look at the problem and they go like, oh, well, we can solve this using something that we have from that area into here, right? So these folks, I don't think are from operating system research. They're mostly from first order logic kind of stuff. So the whole section 2, you have to believe it on trust, right? Because if they say, trust me, you can do this, trust me, you can do the thing, I have no idea what they're talking about in the logic stuff. I don't have enough background in logic to see if they're good or bad, right? So I just have to assume that they're good, right? So from a system perspective, you're only supposed to read the section 3, which magically makes these things work, right? And because I mean, so that's a big problem for logistically, right? Like imagine you going out of whatever you're expert in and going to another area and going to the top conference and presenting something, and you have to be good in both the fields, and that's not a trivial task, right? But you usually get this stuff which is considered sort of beautiful because you're bringing these two fields in, and this one other stuff, right? The other thing I was mentioning was, so these people come more from a theoretical background. The theoreticians say stuff which systems people kind of ignore. So one of the things theoreticians will say is that is NP complete, right? This scheduling algorithm is NP complete. In fact, most of the stuff we do is NP complete, right? But we sort of muddle through with heuristics, and we know that it doesn't work for all possible cases, but it works in normal case, right? So I think that's one of the things they do here, which is it doesn't work for all the cases. They haven't looked at the backward loop. I still don't understand why exactly it doesn't work for a backward loop, but it seems like there's some issues involved. And when they say, I think we can do something about it, I give it to them. And forward loops, they say, we can do that. We don't explain it here, but sort of hand wave and stuff, and we can do that kind of stuff, right? I just give it to them because whatever, right? And they're going the same with the exponential stuff, right? They say it's the exponential in the general case, but if you introduce loops and stuff, I still don't understand exactly what that changes the stuff, but you can make it reasonable, right? The overhead, they say it's 3 times overhead. And the thing can become exponential and all those things. I think within the context of what they're trying to say, I'm willing to give them the benefit of the doubt, right? I don't have pretense to assume that you can put any code into the kernel using this stuff, but for enough class of applications, this seem to work, right? So one of the things is it's exponential, but if you think of like a smaller piece of code, it may be okay, right? So that's still a big piece. I mean, the device driver and all those things are not expected to be a lot. The performance numbers are really awesome, right? 1.4 millisecond. Mind you, this is not the modern computers, right? I mean, these are DEC alphas which are running at 175 megahertz or something, and it looks like it's extremely CPU intensive. I mean, the computations seem to be CPU intensive or memory intensive. So I don't know. I don't have any idea how it will be right now. But 1.1, 1 millisecond to during load time check and nothing else after that. That doesn't seem like a big overhead, right? The memory would be a problem. Memory the thing will be bigger, but it's not the code that becomes bigger. The code that runs into the kernel stays whatever it was, right? I mean, to the most part, the thing which explodes is the security proof, right? And I think that's okay because that's not the part which gets loaded, right? And even the 1 millisecond is okay because you expect this stuff to be used a lot inside the kernel. So if you're not using it at all, then you probably pay the case. And I don't see. I think some of you mentioned. I think one of you mentioned that if you have applications where lots of things are loaded into the kernel, this could be a problem. But I don't think that's what they're trying to attempt. I mean, I think they're attempting to push something into the kernel where you do due diligence and get the stuff in, right? It was sort of hard for me to read because they use terms which make sense from their first order logic kind of stuff, which I need to translate into computer science kind of term, right? So the first section seemed like they were talking about security policies of the system, right? Which essentially seemed like you are creating a policy of how the system ought to behave in a safe, secure manner, right? So you're creating the model of how the hardware should behave if it's performing in a secure fashion, right? You're not mentioning the policy of, you're not saying you're only allowed to read packets from so and so, and like not like the policy that you kind of imagine at the system level. What you're trying to say is, if in a secure machine, you should not be able to modify this register because this register, by certain convention, is being used for something else. So any program that you write should not have to write here, should not have to modify these stuff, right? So you're defining sort of what your legal program should do. And their proof check is really trying to see if your program would do what was suggested that you should do. If your policy says you're only allowed to modify these 3 registers, the proof checks if your code will only modify those 3 registers, right? And clearly, the open question is, what if you go buck wild and you actually try to put the whole alpha security policy, which I don't think they have any clue how they would do, but there must be enough cases where these things are useful, right? So regarding the question, do I know if this is being used? I don't know, because I don't actually work in this area. So I don't know how much of this is being used, right? It may be used. I just have no way of knowing what they're doing. But the citation seems like there's a lot of work, maybe in the programming language community, on this kind of stuff. So I tend to believe that it makes impact, right? A lot of the things that you study in these papers, they take a long time to get into real operating systems, right? Operating system community is not known for, moving the leading edge of stuff into the kernel. It's a very conservative thing because it's a crucial thing. So if you want to change something, so if Windows Vista wanted to change the way drivers are returned, right? That's a massive undertaking, right? They have to figure out what to do with the existing drivers. They have to be able to tell all their programmers what to do, and it takes years and decades for things like that to change. So if any of you have worked on Windows kind of stuff, right? You're not going to be changing Windows Win32 API to something else on a drop. So it may be happening slowly, right? And I misspoke in last lecture where I said we're not reading the Nooks paper. Turns out we are. We are reading it on next Tuesday, right? That's the paper which is follow-up to all the stuff, which talks about how you can load existing drivers into a kernel in a safe and secure fashion. Now that's the next Tuesday. I got confused because the title didn't say Nooks, but I signed the journal version of the paper, right? So there's a lot of work done on this stuff, and because this is a very important problem, right? So before we go into the stuff, I would like to kind of see. I don't want people to get lost on where we are doing, right? So it seems like we are kind of reading kind of all over the place, or they kind of form a logical time frame, right? So I think one of the goals we are trying to see is we are looking at processes and threads and how the notion of a CPU scheduling broadly defined in this sort of a module, right? So obviously we're not introducing the notion of processes and threads and stuff like that because that's in the, I argue, it's an undergrad class, right? So here we're trying to look at the trade-offs in how you implement that, trade-offs and how you move this stuff, right? And I think one of the things you have to remember is for a given task, right? So if you wanted to do something in a machine, the amount of work you have to do is sort of constant whether you use any of the different variants, right? All of them add overhead, right? But you have to do a certain amount of work, right? All they're trying to do is where it should happen. Should it happen in the user space or kernel space? And as we see over and over again, if each of them have their own benefits, right? If you move it into the application level, what exokernel does, it's great because you don't have to worry about the protection. You have all the stuff on the user level, but then you get the performance problem because if you wanted to get the kernel cross kernel boundary, you pay the penalty, right? You don't want to get rid of the kernel boundary completely. You want to get rid of it as much as possible, so you have to avoid the crossing, right? You do understand that you have to have the boundary because otherwise you compromise the safety. So you have to have this thing. So and all these papers are trying to figure out where that boundary should be, right? And I think at the end of the day, the conclusion is I don't think we exactly know where things should be, right? I mean, it seems like each of them have their benefits, and it's up to the next generation of OS developers to figure out where they should go, right? So that's the first part we're looking at, the monolithic versus microkernel, right? And superficially, I never liked the term microkernel because it sounded like it sounds like something is small, which it is true. I mean, the kernel is small, right? But that's missing the point. The microkernel's idea is to make the kernel small so its performance could be improved and all those things. But by doing that, it's making lots of it's pushing the whatever task you need to do to cross the boundaries often, right? If you make a system call and it has to go to the kernel, it has to call the policy engines outside the kernel. So you're compromising on that. So the fact that the kernel is small is important, but the real thing is you're separating the policy from the mechanism, right? And if in the case of exokernel, you push it even further by moving everything into the application space. And in the case of a spin, you go the other way, you push everything into the kernel, right? And if you want to do that, you have certain issues, and in spin, it basically tries to address that using type-safe languages. And this one looks at it from proof carrying codes, and the Nux continues with that direction, right? So those are the two kind of opponents. One is move everything to the application level and mess with something. I don't really believe the critique that I think one of the spin papers said, which is exokernel depends on hardware, right? Yes, but that can be solved. I mean, hardware was not born in a vacuum, right? I mean, hardware works with the software. So if we all like the exokernel approach, that's the way to go, then we have to tell Intel to do whatever is necessary to make that happen, and vice versa, right? But there's two philosophical things. Should we move everything into the kernel? Should we move everything out of the kernel? And we looked at some of the other issues on how to optimize these little stacks and processes and events and scheduling and all those things. So again, we're still trying to figure out how to manage this trade-offs and how to optimize these different stuff, right? So is that sort of clear? We're going to read some more papers on how to do this stuff because it's very important, because your modern system, if you want to get the performance out of the stuff, you have to figure out where these things go, right? And so we know something has to be done. So the question is, should it be inside the kernel or outside the kernel, right? We love to put it inside the kernel because then we don't have to worry about anything. It has access to everything. You don't have to do any kind of performance check. But then you have to worry about the safety, and that's where these three papers come in, right? And in the marketplace, I think it's going more towards the loading stuff into the kernel, right? Most of us use DLLs and modules and kernel loadable libraries and stuff like that. So people like monolithic kernel for the most part, I would think, because that's an easy abstraction to program with. I mean, programming through a POSIX API or something, it seems like an easier thing to deal with. And even though like Apple Mac OS X is a microkernel-based system, I think a lot more programmers use it as a POSIX system or the quad system, but not necessarily building their own microkernel interfaces, right? So in a lot of sense, the notion of the three papers that we're going to read, the spin and the paper today and the Nux paper are very relevant, right? And actually, the Nux paper will give you a lot of statistics on how awful the performance of modules and the loading stuff into the kernel, right? You have to use one of these stuff or you're in trouble, right? Right? So again, what's the problem that is being addressed, right? I think it's the same as what spin is doing. It's sort of like a follow-on to spin, which is kind of surprising because it followed up the next year. Spin was in 95, this is in 96, right? So they were kind of, they didn't explicitly follow on, but implicitly followed on, right? So their model is spin achieves safety by using modular 3, right? So it uses the programming language to do static checks to make sure that you don't do anything bad, right? And I think one of the things we agreed is spin. The problem is you have to use modular 3, right? Or some language which enforces that. So if you want to write something in assembly language, then you really cannot do that because you have to be able to type check assembly language, which is very hard, right? So their model is you carry this proof carrying code, right? So the notion of proof carrying code is you kind of create a model of what the system should behave, right? You create a security policy, which sounds like a policy, but essentially what you say is you build what the system is allowed to do as a first order logic entity, right? You give it to the kernel and you give it to the application developer, right? The nice thing about how this works, which goes into the first order logic, is this is all encodable and usable by mere model. So it's not like a tree data structure, but it's some data structure that is pseudo efficient, and you give it to both of you, right? So you write your normal code the way you want, right? So the question is, should the programming the language that you write should it be higher level language or assembly language, right? They only showed it for hand coded assembly language, which I would argue means that they are trying a harder case than making it into the compiler, right? Though they haven't proven anything, right? So you could argue that writing optimized code would be harder than using a compiler, because compiler you expect it to be far more predictable than a hard hand-coded assembly language. Of course, they don't prove or disprove either way, but my gut says that it'll be harder to do this for hand-coded assembly language, right? And they're only able to check certain things, right? They're able to check the memory safety and all those things, but not necessarily other things which they say they could do, right? You know, whether your resource allocation is fair or something could be done, but they haven't done it, and that's, you know, that's not worth harping over. So basically, when you write the program, right, you generate a security proof based giving your program and the policy you have, and then you generate the stuff, right? And they show that in general it's not possible to do it automated, but in some small cases you can do this in automated case, right? And we can't punish them for kind of punting that, because automated means they have to build a compiler, right? So you can't expect one student to go off and write a full-fledged compiler. I think they did something to have some sort of automated stuff. I mean, they claim that it's automated stuff, but you basically have to build a whole compiler environment to show what you can do in automated fashion, right? And yes, you can't do that for all the cases, but you can do it for some cases, right? So, and then you give, and the key to remember is your security policy or your interpretation of the machine should do will restrict what the hardware can do, right? The hardware itself allows you to do anything. The goal here is to say you cannot do certain things, right? So your hardware may allow you to write into any register, but your security policy may say you're only allowed to write into certain particular registers because certain other registers are used by somebody else, right? So you have to have precondition of where the system will be. So you have to say, when the system comes to you, this is how the system will be, right? From that state, and this is how the post condition should be. You know, if I use those stuff, this code will not, essentially, behind all the logic stuff is they're trying to find out whether your code will modify something, modify or do stuff that your security policy says you cannot do, right? So if your hardware is not allowed to modify certain memory, which is not, certain things, if it tries to modify that, you'll catch it, right? So this is a lot more powerful than you signing the object, because it basically technically goes through your program and sees whether what you're modifying and whether you're modifying something you're not supposed to modify, right? Which is a lot more harder than signed certificates, which basically says that this came from you. So if you wrote a piece of code and go to Microsoft and says, I want you to sign it, and they sign it for you, that basically says that this code came from you, signed by Microsoft. Whereas what they're trying to do here is, it tells the kernel that here's a piece of program, right? This program modifies registers and memory locations in some undefined fashion, right? You can verify that this program will not do anything that you didn't want. So if you specify the right security policy And if you give me a program, I can check to see if this one won't violate that, right? And clearly that's non-computable in general case, right? If you can do that, then you can do this for any programming language. I can then give, say, I want to give PowerPoint and give the specification, and then out comes it, you can say whether it's doing what it's supposed to do. So in the general case, they can't do that. But in a restricted case, they argue they can do that. And they show, at least in the restricted case, they can do that. And they make arguments that why it's not so restricted. I mean, you can go beyond that. I just don't think you can use this to prove whether PowerPoint is doing what it's supposed to do, because that's far too complex, and it's not intended to do that. I mean, for a little piece of code, they can do that, right? So the strength here is your kernel can prove that this code will not modify something that it's not supposed to, right? So the challenge is you have to come up with a security policy which is sort of reasonable and sort of, for you to specify that, right? And again, that may or may not be hard for real cases. That's for us to figure out. At least for the little IP tables things that they do, they argue that it's not very hard, right? The security community and the programming community will argue that if you don't understand what is legal and what is not legal, you have no business writing code, right? Do you buy that argument? So all this depends on the belief that you can build the security policy, right? And I don't think there's any way to audit the policy to understand what it's doing. And there is no claim that this policy is easy to read for mortals, right? I mean, it seems like you have to really know what's going on to come up with that policy. It's not like a Joe Schmo programmer is not going to be able to articulate that in the way that they wanted, right? Right? But do you buy that argument that if you don't know how to write that, you have no business of writing device drivers? Is that important? You think it's an important assumption in this whole thing?
Well, it's an assumption in this case. I don't know if I really buy that from an overall standpoint. I mean, wouldn't it be better if, whether it was the APIs or what, they were written in such a way that they would prevent somebody from malforming the code?
So that's excellent question, and I suspect the answer is somebody can come up with a security model for the entire alpha machine, alpha hardware, and what it can do, a generic thing, right? But I suspect that it'll be so they can generate this library and give it to every programmer, right? But I suspect that each application would want to restrict that general thing into something smaller and manageable, right? The way they explain the IP tables, right? There are certain rules, right? You can only modify this header, you can only modify this, look at this field, you can only do certain things, right? That is far more restrictive and far more simpler compared to what a generic device driver should do in alpha, right? A generic device driver should be able to do more stuff than what this IP tables does, right? So the challenge is, would you be able to do this generic thing which says, in general, this won't mess up anything, right? So clearly, no driver should be able to modify something in another module. Let's say that's apparently clear, right? So that can be encoded in the generic policy, right? But their particular policy says you're only allowed to look at certain fields, not certain other fields, right? That won't be a generic policy. That will have to be customized, right? And I have no background in compilers to know that can be expressed by easy term, by saying you're only allowed to look at these memory stuff, right? I suspect that it's an active area of research. I just don't know if it's computable or not, right? That's a big challenge. I mean, so it all depends on you coming up with that policy. If you can't come up with a policy, then this thing makes no sense, right? Because I think the other stuff can be automated. I mean, I believe their argument that you can automate some of the stuff, right? So once you have the policy, you may be able to have a compiler assembler which will check which will create the proof based on the policy and your particular piece of code. I just don't think that That seems like a very hard thing. So let's assume that it's very hard and somehow you should be able to do that. But there's a line of thought which says that somebody ought to be able to do that. If you can't, then you can't expect anything out of the system. If you cannot articulate what the driver should do, and the kernel cannot articulate, actually it's the kernel which develops that, right? So the kernel has to say, you as a device. So the way it should work is Microsoft should say, if you are writing a network driver, right? Here's the policy that you have to follow, right? Here's the policy we give it to you. So it's not given actually by the application, it's given by the kernel, right? So if Microsoft cannot do that, then this paper is not for us. I mean, if they can't do that, then we cannot do anything. But let's assume we do that. But I suspect this is going to be very hard because I don't think it's easy to prove or disprove whether it's doing the right thing and understanding those things. But anyway, so you do that. But the beauty of that is once you do that, this code actually checks whether your program is doing what it's supposed to do, which is much more stronger, which I don't think they actually make it as strong a claim as I would have liked to, because that's why I was disagreeing with you, because they say it checks whether this policy is matched, right? But it's actually they're checking whether your program would ever modify anything which violates that policy, right? But the way they implement that is through other logic mechanism, but essentially that's the net result of that, right? So you take you write a piece of assembly code, you take the policy which is available to both the kernel and you compute the safety proof, right? And you send both to the kernel, and clearly the safety proof is bigger than your program, right? But it's not a big deal because safety proof is only necessary to check this stuff, right? So you give both to the kernel. So the kernel takes your program, right, and computes a safety predicate using it computes a safety proof, right? And then, it computes a safety predicate, and then it checks the safety predicate against the safety proof that you gave, right? And if it ran to completion, that means this particular safety check, this particular piece of code is safe, right? So all the kernel needs to do at runtime is be able to take the safety, be able to take your program, which gave it, and using the security policy, it generates a safety predicate on the fly, and then it checks whether the safety predicate matches the safety proof, right? And then they claim, which I didn't understand what exactly was happening, that this is basically type checking, right? The checking whether the safety predicate matches the safety proof is basically type checking, and type checking is very easy to do. So you can actually build it in five pages of C code, and that's pretty fast, right? So the logic magic is this whole thing can be done very quickly using mechanisms that I don't understand. But the idea is you can do all these things very fast, right? So they don't claim that generating the safety proof is simple, because there's no motivation for it to be, there's no need for it to be fast or whatever, right? So it may take you months to generate the safety proof. All you want is the kernel to be able to generate the safety predicate fast and be able to check whether the safety predicate matches the safety proof. It could take you as much time to create the safety proof. That's okay, because that's done offline. So that's as part of your generating your driver, you generate the safety proof, but the running kernel only needs your safety proof and the program and the security policy to come up with a safety predicate and be able to match that and see whether it matches. If it matches, then it can guarantee that your program is safe, meaning your program will not modify, under no circumstances, absolutely will not modify anything that you're not supposed to modify, or do some things you're not supposed to do, like read or write what you're not supposed to do, right? And it's apparently fast. I mean, 1.4 millisecond I think is very fast, because this is not exactly the modern machine. So in that machine, this is fast. And they argue that it's highly unlikely, and I think one of you had a problem with that. So essentially, if you modified the code, right, the safety predicate that it creates may not match the safety proof, right? Except if you modify it in such a fashion where it will still match the safety. So if the modification still matched, so you're allowed to modify it into another program, right? If it still is true to the security policy, this will match, right? Because security proof only says that this piece of code would honor the policy. So if you code rearrange or whatever, and if you do, so if the predicate that you create will still solve the problem, still solve security policy, then this particular piece of code will be allowed, right? So code rearrangement would be okay, but you're still not violating the safety of the stuff. The other ones, nobody has been able to break the stuff, so we have to assume that it works, right? And some of you had a problem with that, but if you look at security literature, that's basically what they do, right? I mean, security is basically based on, we just don't know how to break, we just don't know how to do certain things with prime numbers or what have you, right? So it's the security folks' way of saying, I mean, that's the guarantee that they give, right? If you look at any security literature, they don't give you a guarantee that this thing is unbreakable, right? All they can say is, given what we know, it looks like we cannot break it, right? So till someone figures out how to break them, we have to assume that it's unbreakable, right? And if it stands the test of time, you just go with it, right?
Well, I thought they went beyond that, though. That's the thing.
Right.
It wasn't just that they said that we don't know if it's breakable, but they went ahead and they contended here that tampering could go undetected only if the adulterated code is still guaranteed to respect the safety policy. They didn't give any rationale for why that's
because I think the rationale is when you create the safety predicate, you take the code and the security policy, right? You don't look at anything else, right? So you take the security policy is there, right? Which is both to the kernel and to the user, right? So the kernel takes the security policy and your program, right, to generate the predicate. I think the argument is it doesn't look at anything about the security code. It doesn't look at anything at the security code, right? It just looks at this predicate to see if this one follows the security. I keep mentioning the
proof is actually
security proof.
Yeah.
Yeah, the security proof, right? I think the understanding is security proof says that this piece of code is following that policy. It doesn't say anything about that particular piece of code. It just says that whatever code you give me, right, for the security policy and this code, if it matches the proof, it's verifying the correctness of the initial assertion, which is the security policy. Nothing to do with the proof itself.
Well, if it's computing the predicate, that wasn't quite the way I understood. I see what you're saying there. It's actually looking at the program code, the source code,
Yeah.
and computing a predicate
Yeah.
to make sure, and the predicate should tell it whether it's going to be valid, whether it's going to cause any problems.
Yes.
Why does it need to compare it against the security proof?
So I don't understand the exact reasoning behind it, right? So you have to. So my understanding was this security proof proves that whatever predicate you generate is compliant to this policy. I think the security proof is a more general case of proving this stuff, not particularly this code. Security proof, I don't think requires your program to prove something. Security proof basically says that, I think the model is, if you know how to solve this problem, if whatever you generate can prove this stuff, then it basically proves this stuff. Right? So I think basically if you have a security policy, you create a security proof which does not require the program, right? Your transformation is you take the security policy and create a security proof. Is that true?
I think it's because you generate the safety predicate for the code, for the program code, but then you also have to generate a proof that the safety predicate is actually safe.
Yeah, but I think the proof, so I think my contention is the safety proof is generated from the security policy.
Right. And
not from the program, right?
And this doesn't guarantee anything about what the code does.
No.
Other than that, it doesn't do what it's not supposed to.
Yeah.
And that's the whole point, is that multiple things can have the same predicate because they don't do what they're not supposed to do.
Yeah, so that's important to understand, right? This is not this is not proving that your program is doing what it's supposed to do. It's proving that your program will not violate the security policy, right? So your security proof basically says that, somehow you generate, I don't understand the mechanism, right? So magically you take a security policy, you create a security proof, right? The assertion here is anyone who knows how to solve the security proof is safe, right? So you take a code and you generate a security predicate. That means this one can solve this particular problem. So all I need to give you is the security policy and the proof, and any code which can solve this proof is safe. Meaning that you won't access something that you're not supposed to. You won't do something you're not supposed to do, right? You may do wrong things, but that's not what you're concerned, right? So you may have bugs in your code, but your bugs will be safe. So what we're trying to do is protect the kernel from you, right? You're giving me a piece of code. I'm going to run it inside the kernel. All I'm guaranteeing you is you will run it safely inside the kernel, and you won't change something you're not supposed to do, right? So what are the kinds of bugs that can happen when you give me a driver?
You could reformat the hard drive.
Yeah, so you could reformat the hard drive, and another kind of things.
Would that also check for like Stack Overflow in that?
So if your policy can, yeah.
Mm-hmm.
So for the kind of things that you can do where you mock up some data structure, either read or write, these things will catch, right? So if you want to go into a while loop doing nothing, these things won't catch that.
If it were just a logical error as well.
If you can encode that logical error case,
but I mean, if you're really supposed to check to see if the number is equal to 0, then do something.
Oh.
Otherwise, do something else. Whereas instead, you said if the number is not equal to 0, do something. Otherwise, if it's equal to 0, do it. So if you kind of flip things around like that, you probably couldn't encode that in the safety.
I assume that, yeah. I think you can't do that logical error. I mean, so yeah, there are some things you can't do, right? Which I think, like, so if you have programming error, if you're going through a while loop or something where you don't touch anything, you just do while one, this will happily let you go through because you're not violating security policy, right? You're doing something dumb, but you're not violating security policy. So I don't think it can check for performance bugs. I don't think it can check for program functionality correction, right? All it says is whatever you modify, it can't do what it's not supposed to do, right?
Didn't they say something about being able to extend this to work with time usage?
So they lost me on that one, right?
So I mean, theoretically, you could see performance issues if you.
So yeah, you have to be well versed in first order logic to know what they're talking about, right? So it all boils down to is as long as whatever you want to do can be mapped into first order logic, you are good. If it cannot be mapped, you cannot do it. So whatever you can do. So clearly checking whether you are reading the right memory or route memory can be done. That's what they showed. That's what they claim. Other things, some of them they speculate you may be able to do those. I have no reason to believe either they can do or not do, right? But I think those are two different issues, right? Seeing if the kernel, the driver that you're loading has a bug that gives you bad performance or does something which is not what you wanted, that's a different problem. All they're trying to say is I can safely load it into the kernel and do stuff. You may cause performance problems, but you won't bring down the machine because you're accessing something you're not supposed to do, right? So that's the logic. So they're not solving the problem of would this do, because I think that's impossible, right? Making sure that this is doing the right stuff, which is where they come up with it's uncomputable, right? You cannot take a piece of code and then prove or disprove what it's supposed to do, right? I'm paraphrasing. If you take a theory class, they'll exactly tell you what that means.
It depends on if you restrict the language, but if you make it if it's
which is what they do, right? I mean, they're restricting what they can do. So I'm saying that's a theory of computation class, right? Where you will precisely know what they're talking about, right? So yeah, in the general case, you can't do stuff, but I think that practically they can do a whole lot of stuff. So I think the beauty is somehow you generate this stuff, this proof from the security policy, not from your code. So basically when you give the security proof, you're not proving anything about this particular code. You're saying any code that comes with it will have to, will need this proof, right? So if you take the same security policy and if you have two different programs, I think they share the same proof, right? So you can have one proof which basically says that anybody who runs this program ought to be able to do this stuff, right? And for reasons which I don't understand at all, is this can be done using a type check. So they basically say, essentially this is basically a type check, and a lot of the things have to happen. You need to be able to kind of merge this predicate and the proof. You need to be able to generate a predicate and then do something with the proof and then kind of check those stuff. And they say that's like basically a type check, and the proof is exponential because it creates a tree, right? The predicate seems to be small. The predicate is not that big as the proof, and somehow they do that, and magically this happened, right? So I think the security claim I think is valid, right? As long as this is true, right? That somehow if you solve the proof, if any predicate can match the proof, then that means you're following the policy, right? And I have no reason to be skeptical because I have no idea. I mean, to be honest, I don't know first order logic. How many of you have background in first order logic? And so actually there's only one person who.
It's from AI, artificial intelligence.
Okay.
So you use that in games.
Okay.
Something like that, when you have like lots of rules and all.
So is that what is my explanation?
I'm not quite sure, but it sounded familiar to me.
Okay. So we need somebody who's like way beyond that, right? Somebody who's like breathing first order logic to be able to kind of understand whether this makes sense, right? I have to defer it to the people who reviewed this and who seem to be thinking highly of this one, right? So somehow you can do this stuff, right? And this is probably what it does, right? So if you modify the proof, then then your code will not match that, so it won't be loaded. But so that's their logic, right? The logic, so you give the security the proof and your code, right? The kernel has to generate the predicate itself based on the policy, and then you can see whether the proof can be done. So I got the author's slides. Unfortunately, I don't remember. I didn't go to this conference, so I don't remember what they talked about. So they think this is useful for OS extensions, safe mobile code, programming language interoperation. Therefore, programming language folks, and essentially you send the native code and the safety proof. And I think this slide was they were saying this and this was their contribution, right? The slide has this hanging, but it's basically for those. So they were trying to explain this stuff, right? So essentially you have some policy, right? The policy is if you are able to get over here and get out of here, it's safe, right? So the safety proof is essentially generating this maze, right? So any path which takes you from here to here is safe, right? This does not mean, so if you wrote one program which can go through straight, you have another program which goes through this for days before it comes out, that's not what it's trying to show. All it says is, the proof says is, if you can get in here and if you can get out, then it's safe, right? And a particular safety predicate may be this particular path for you to get out, right? So if you modify this program to make it go through some other path, you change the program in some sense, but if you can still go through the maze and get out, then it's safe, right? And
so intuitively what that means, I guess, is that you can actually change the program. You can generate, if you have a minor bug in your program that doesn't really affect the safety of it, but generates the performance of something, that you can actually use the same proof after you fix the bug without necessarily having a change.
Yeah. So yeah. So in fact, so is it true then? I'm just asking that given a security policy, you can create a security proof once, right? And never ever modify it. I can generate multiple drivers with the same thing. Is that true? Multiple different filters, basically programs, right? To have the same proof, right?
That's what it seems to be saying, and that's what worries me, because I'm just having trouble with that concept.
Yeah, so I agree with you, but I think that's because we don't know how this first order logic works, right? So it doesn't look like any of us is really qualified to appreciate that assertion, right? But let's assume that the assertion is true, right? Which I think is true. I mean, so because by way of, people seem to have bought it, so let's assume that it's true, right? So if that is true, right, then essentially so all it says is it creates a security proof, right? So you can use a security proof for any amount of modifications of the code,
I
right?
guess it's like if you don't allow backtracking through the maze, the predicate states the way that every single decision that you're going to make, and it's easily generated from the code, and then you can see if that matches the maze, and the maze will block off certain parts, certain aspects of itself, so that you can't actually get from. If you decide to go left, then you can't actually ever get through because deciding to go left means that you did something bad. So since the predicate actually is a path through the maze, what you're actually generating from your code is a path through the maze, and if your path makes a wrong choice somewhere, then there's going to be a wall in the way, and you try to cross a wall boundary, which you're not supposed to do.
Yeah, then you block.
Right.
They say when there's no decision, you just block, and then so basically, if it completes, then it's proven. If it doesn't complete, it's stuck in the maze, and that's the indirect proof, right? So they do give details of how this works, right? So this is, so I'm suspecting that they say these are the things that can be done. They have shown these ones, they just believe that they can do that, right? So memory safety, which is what they show in this particular paper, can be done. Data abstraction boundaries, again, as long as it's mapped into some memory stuff, you can do that, right? Concurrency properties, resource usage guarantees, they believe that they can do that, right? And I mean, whatever, right? I mean, it depends on whether you can build the proof for those problems. And they haven't shown this, but maybe it's possible, right? So let's ignore that. They show that it works for assembly language. They haven't shown whether it works for high-level language. My gut feeling is if it can work for hand-optimized assembly code, it can work for anything, right? But of course, I have no proof that that needs to be true, right? But I suspect that hand-optimized assembly code is a lot harder to deal with than high-level languages. I have no reason to believe that, right? I think the hardest part in the system is not this component, it's coming up with the security policy, right? Coming with security policy means that you need to kind of understand exactly what this machine is supposed to do. It's very machine dependent, it depends on particular alpha. You have to know how the things work, and who saves registers, what registers are supposed to be used, and all those things to be able to specify the policy, right? So any policy violations will have to be articulated. If you don't, then it won't check it, it's not done, right? So you need to know what memory locations can be addressed, and that is the hardest part. That they don't even attempt, I mean, it's not possible for them to attempt that. I mean, they cannot show that it's easy to do because by definition, if they don't know how to do it, no one else in the world can do it because they're the ones who are proposing it, right? But since they can do it, doesn't mean anything that normal people can do, right? So that's the hard thing. But anyway, so that's the thing. And tamper-proof, it depends on properties that we have to assume that it's true. And it's simple and fast and easy to validate because of the stuff they say. So at least for this particular example they show, it's fantastic. And if you look at the performance, they're doing an excellent job, right? I think the main contribution is to show that this is a new kind of stuff. So the reason why people are excited about this stuff is not that this is the, so in terms of publications and stuff, right? If you're the nth paper of some new concept, life is a lot easier because you know the parameters of what you're trying to do, right? Being the first one to propose this stuff, you are coming up with all sort of stuff along the way, right? There's no basis to form, right? In fact, they didn't even have a formal related work section, right? As far as I saw, there's no related work section. They kind of, when they talked about like Java and stuff, they can't do that kind of stuff, but it's sort of like that, right? So I don't want to kind of overblow their importance, but it's sort of like the Einstein's theory kind of stuff, right? There's no prior work. You just go along. So some of the stuff that they claim is you have to be skeptical, but I mean like breaking new ground kind of stuff, right? So So it's optimized for the deck alpha, so it has to be optimized for the deck alpha kind of thing. And so the safety policy here is given to them by the Berkeley packet filter, which says that what you can do, what you can write, and all those things, so you can encode the stuff, right? And the key here is to have this policy and be able to translate that into something. So you need somebody who's really good at doing this stuff. So it's not something that normal programmers can be expected to do. So they added this first order predicate logic, can read and can write. I don't understand the conventions that they use, the symbols that they use and stuff, and they make no effort, because clearly they cannot explain to me what first order logic is in one single paper, right? And that just how life is. One of the reasons why I like this kind of paper is in your career you'll see some papers which come from another field, and then they solve something which is so elegant, you have no way of understanding what really happened, right? You have to believe that these things work, but once you believe those things work, this thing is so beautiful. And the annoying part is you can never come up with a solution because you have no idea what that other stuff is, so you kind of solve the stuff, right? I've seen this with one of my colleagues when I was at grad school. He was working on his PhD thesis for a while. He was coming to the heuristics for solving some problem. And somebody else published a paper. They used Bloom filters to solve what he was trying to solve for 3 years. And Bloom filters turned out to be this beautiful data structure where you encode. So his problem was he had a directory of some things which he had to give to the different nodes, right? So you had to say, I have ABC, you have BC, and you have AC. I want to know what everyone has, right? That's a directory problem. So I want to be able to send my directory entry to everybody, and it keeps modifying, right? So the key is, if I send the whole thing over, it's really big, right? And he was trying to figure out how to solve the problem. It's a distributed systems problem. You want to deal with it. It turns out you can create a Bloom filter out of that stuff and send it to everybody else, right? So the whole problem just goes away if you use a Bloom filter, right? You have to understand how Bloom filters really work to understand the limitations. But if you bear with me and say, Bloom filter basically takes whatever size data structure you have into this small compact data structure, right, with certain restrictions, and I can send it to you, right? I can make it into like a 64-bit number or something. I can send it to you, and that shows whether something belongs in that set or not, right? With limitations, right? But I'm saying that makes the whole problem so elegant, because before you were trying to see, should I send it in gzipped it, or should I do blah, blah, blah kind of thing, and here somebody comes along and says, nope, all you have to do is do a Bloom filter, simple, send it across, and the smaller the Bloom filter is, the less accurate it is. The larger it is, it's good, right? And you solve it in one swoop, right? Then you can imagine how frustrated he was. But it's still, I mean, you're frustrated because you spent last 2 years, 3 years trying to solve it in the brute force manner, and somebody comes up and says, all you need is this first order logic, which I have no idea what that is, but seems to do what you want to do, right?
Don't we do that in cryptography with one-way hashes? I mean, at least for me, I have no idea why the mathematics works the way it does.
Oh yeah, I mean, security, that's the problem of security. That's one of the things I was saying, right? Security, they say, the whole thing works because you cannot factor this number, right? Mm-hmm. To be honest, I don't actually understand what factors really means, right? I don't pretend to understand what that really means, right? But you have to believe that, right? You have to believe that these things are not factorable, right? And if you try to ask them why, they can't explain it because their answer is, no one has been able to do it so far, right? And so the whole, as far as I can tell, the whole security sort of beliefs depends on this belief that this cannot be done, right? They couldn't explain to me, because I don't understand, even if they try to explain, why it's the case. But once you believe that, then everything else is easy, right? But the people who work on those, the concept of what this factoring and all those things, right? I think there's a lot of stuff here. I mean, it's magic. And so if I were to review this paper, I have to give up my hand because I have no way of evaluating whether these are good, right? So one of the things that when you're program committees and stuff is getting these sort of papers is very hard to evaluate, because if you're in the first order logic world, they probably think that there's not much to it, right? So if you're in the programming language community, they will be like, we know all this stuff. I mean, you don't have to tell me that they are using flight sale verification, because flight sale verification has been known for a decade, right? For 2 decades, right? So they know I don't think there's too much interesting from the logic perspective, right? The interesting stuff happens when you apply that to some systems problem, right? So for example, the notion that the predicate should be able to, you need to be able to compute the predicate fast is not something that the logic community would care, right? If you're working on the logic and proof and stuff, you don't really care whether this thing can be done fast, except you want it to be done within a lifetime kind of thing. They're not really worried whether it's 1 millisecond or 10 millisecond, right? So from the logic community perspective, I suspect that all this stuff is well known. It's not a big deal, right? From the system community stuff, we don't care about all those. We only care about the speed perspective, right? So finding some person who knows both to say, well, the technical merit of all the stuff that they're trying to do is still valid. I mean, somebody has to understand that Floyd cell verification does do what it's supposed to do, right? And then be able to appreciate this stuff is very hard, right? Because if you're having difficulty, the same thing happens with the program committee. There's nothing to fall back on because nobody else has done this before. So you have to say, I have to trust the authors, and you don't want to trust the authors. And how do you deal with that, right?
Well, they need to carry some proof carrying code around to prove that they're,
So usually you give it to a programming language person, right? And they come back and say, all the stuff they're saying is elementary and true, right? And they come up with like, but they shouldn't use Floyd style stuff. They should use Ike style stuff, right? I'm just making up some hurricane name, and they say, you should use Ike style stuff because that one actually has a stronger proof than this, right? We don't know what that means because whatever, right? But what you really want to know is whether Ike style would still be able to compute faster, right? Which they won't know because that's not what they care about kind of stuff. But so anyway, so they did apparently talk about this in the conference, but I imagine most of the audience had no idea what they're talking about in Floyd cell verification or whatever. So you just assume that all the stuff they say is true. So essentially, you create this tree which you can't read here, but essentially that's the proof tree, right? I have no idea how to even read that stuff because most of the symbols I don't recognize, right? Plus with the circle, minus with the circle, and all sort of stuff. But anyway, so this tree, this proof basically is the maze, right? It basically says that it takes your policy and it creates this proof, and if you can solve this proof, then you're good to go. So then, of course, you use the Edinburgh logical framework, and so you encode it in that expression style. But essentially, the key thing that I want to know is this is essentially type checking. So you can now take this predicate and then check it against the tree that they mentioned using type checking. And it's simple and fast to code. There's only 14 rules, 5 pages of C code, and they address one of the concerns that you had last time, which is if you don't trust somebody else's code, you can write your own type checker because it's that simple, right? You don't have to believe us. If you really don't want to believe us, write your own code. It's only 14 rules. It's just like we wrote in 5 pages of C code, and essentially that can check whether. So a kernel developer can develop their own type checker, which does the Edinburgh logical function, right? And of course, I mean, the challenge here is it might have been explored from the logic, the computer, the programming language side of the world, but not from the systems world where you want to make it practical and be able to run and all those things. So I mean, there's a lot of things to do, and they did an excellent job. They checked it with the software fault isolation techniques. They used Modular 3 and Berkeley packet filter, right? And I really liked the fact that they did that because one of the things that you realize, one of the things you probably realize from your project and everything, is all these research prototypes are not something, you don't ask like, so can you send me Modular 3, right? Usually the answer is, yeah, we can send Modular 3 and here it is in a bunch of, we just wrote it on a piece of paper, here have it kind of thing. Right? There's no instructions on how to do that and stuff. So they need to understand how to bring this compiler up on the machine and stuff. So in terms of logistics for students, which you guys will face along the road, which is each one of these steps takes a lot of time, right? To build a Modular 3 compiler and modify it enough to do what they need to do to check the stuff. They don't harp on that, but it's not a trivial task. You need to, it takes a lot of time for you to get up to speed to, because if you do something to make modular 3 look awful than it really is, people are going to, so one of the things that, which is human nature is, if I'm in the program committee and I suppose I happen to be the one who's writing modular 3, and here you show this graph which shows that I'm awful, right? Even though I should not feel awful about it, human nature will all say like, nah, you know. So if you had used this modular 3 with minus OS option, you are good, right? So I'm going to argue against this paper because you're showing that I was not fast, right? You can argue that I shouldn't care about it because whatever, right? I mean, that's the right thing to do or whatever, right? But human beings are what they are. So you want to make sure that they're doing excellent job with that. They're doing excellent job with all the stuff. So the other people in the community, the existing people are likely to be on the program committee, right? The people who believe that PCC is the way to go are not going to be in the program committee because it hasn't been published yet. People who are in the community are going to say, I don't believe that modular 3 is slower, right? So you have to do excellent job of doing the stuff. So so you have to give them credit for trying to do the stuff, right? And because this graph, if you show it to me now of the modular 3 developer or BFF or whatever I am, I don't like this graph, right? Because there must be something that you messed up to show that I'm kind of poor. But I don't see any reason why they shouldn't be good, right? Because the beauty of this whole thing is, if you buy into all the logic stuff, which basically says that the kernel, when it tries to load it, it creates a predicate, checks the predicate against whatever, and then does nothing. It gets out of the way, right? Your native code at that point can be loaded. It'll go as fast as possible. There's no overhead. There's no runtime checking. There's no static checking. There's nothing. Your code at that point is free to do whatever it wants, right? Because the system let you in, which none of these other systems can do because they have to do some sort of a dynamic runtime check because they're not checking those stuff. So this graph does not surprise me because this basically says, what does this graph say? It says optimized code can be fast, which is what it shows, right? It does not show anything about it says that they wrote a very optimized code. If they wrote even more optimized code, which brought it down to a single line, that's what you'll see, right? If you don't know how to program, then this code will be bigger, right? So that's the thing, right? So the key to remember here is not, they show the comparison, right? But they're really comparing the wrong stuff. I mean, it makes you feel good, but what they're trying to say is, if you wrote optimized code tend to be fast, and that's what happens here, right?
Well, that certainly is the case with BPF because they're using an interpreted code there, an interpreter.
Yeah,
I mean, and that's natively going to be slow or naturally going to be slower.
Yeah. So I'm saying it makes you feel good, but exactly, right? I mean, so you're comparing the wrong stuff, right? I mean, modular 3 has this overhead because you're comparing hand optimized assembly code with interpreted code or modular 3 code or what have you, right? But all it says is, when you're running this test, this PCC is out of the way, right? PCC is not involved here. So at this point, PCC has no overhead, which is not surprising at all because that's the whole premise of the whole thing. Once it let in, it's free to go. There's no more checking, nothing. So that's that, right? But it still makes you feel good to see that it's running faster, right? This is more of what you want to see, like the size and the validation times. And I don't want to go too much into the details of the stuff because it seems like it's a reasonable thing. I mean, I'm willing to believe that it's a reasonable piece of stuff. And the real challenge is something that you guys pointed out, which is how can they take it beyond packet filter into other areas? Can they do it, all those things? So at that time, this becomes important, right? Not just for this one case, but if you do it for 10 different scenarios, what's the cost, right? And reasonably, you cannot expect them to do all of those, right? Yeah.
I think the kind of surprising thing to me was that 8 instructions. I assume that it was 8 instructions. The validation time was only, or 362 instructions.
No.
I'm sorry. The proof size is 160, and the validation time is 362.
Mm-hmm.
But you add 300 to the proof size, so you double it, and the validation time went up by a factor of 5 or 4.
Mm-hmm.
So I And that seems relatively small even so. And then it's 420 bytes for the proof for only 28 instructions. What happens if you get something that's like a couple hundred instructions? Are you going to have a couple K, which takes a couple minutes